And yeah, I mean, people can have bad trips, they can have bad experiences, and some doctors are saying, well, even if you have a bad experience, as long as you're guided and there's somebody there who knows what they're doing and that can help you through that, that you're still going to have the beneficial effects of the drug. But others are saying you might get you might get traumatized by that experience if it's really frightening. And then there was a case of a patient who then started having PTSD from that experience and new anxiety disorders around that. So it's important to keep those things in mind. I think also you have to look at it wouldn't be a good idea to give these to people who are prodromal or who have the propensity towards schizophrenia, because or has any sort of history of psychosis, that there might be issues there. So there's definitely caveats, and some people can have bad experiences, and we're starting to learn about, we need to figure out exactly who are the best candidates for this kind of treatment and who do we need to exclude, and that's still a work in progress.
Well, if I can first start off by welcoming you, Dr. Berlin, to the Happy Habit podcast. You are a cognitive neuroscientist and a clinical psychologist. What does cognitive neuroscience involve, and why is it important for our understanding of the mind?
Well, cognitive neuroscience is actually a relatively new field. It really started coming into existence in the 1990s. I was fortunate enough to do an interview with Michael Gazzaniga, who coined the term, or so he says. He and a colleague were in a taxi and they had been drinking a little, and they came up with, why is there's a society for cognitive science, there's neuroscience, but, merging the two. And the idea is that, the brain and the mind are intimately, interconnected. And for many years, it was like these siphons, these disciplines of the science of the mind, or cognition, the way we think, and psychology, and then neuroscience, which is kind of like the hardware in the brain. But this idea, and I was always interested in it, and starting when I was a student in the 90s, was like, oh, I really wanted to study the relationship between the human brain and mind. And when I was in college, there really wasn't, you couldn't do a major in cognitive neuroscience. There was just either your psychology major, neuroscience major, which was much more like, basic neuroscience and molecular. So I ended up majoring in psychology, but I was pre-med, so I took all the sciences and just, kept trying to find the way to what discipline, what could I do to merge these things? And I discovered the field of neuropsychology, which is kind of, before we had a lot of imaging techniques, it was really like trying to understand what's the underlying neural basis of when somebody gets a brain lesion or has some sort of brain damage, and how does it affect their cognition? And you'd make these sort of cortical maps and figure out where in the brain the damage was and how that correlated to a particular cognitive or emotional deficit. But anyway, this field of cognitive neuroscience basically merges the idea of how the brain and the mind are interrelated, and it's a whole field of research using a variety of techniques like neuroimaging, cognitive testing, etc., that can help us, answer these big questions.
The neuroimaging techniques that you were alluding to there, is one of those is the fMRI, is that correct?
Yeah, that's the functional magnetic resonance imaging. Yeah, which basically looks at, it's a way of measuring blood flow to different parts of the brain, and then we use that as a proxy measure. The idea is that where the blood flows is where the most energy is needed. That's where the neurons are firing. So it's really, we're assuming that neural activity is correlated with where the blood flows in the brain, and that's what we're actually measuring with fMRI.
And this is real time as well.
Mm-hmm. Yeah, real time. So, but usually you give a person or a patient a task to do, and then you look at their resting state, sort of when they're not doing anything, although the brain and mind is never really idle doing nothing, right? When you're not doing a particular task, you might be daydreaming or thinking about, what you're going to make for dinner. But you take that sort of resting state where you're not actively engaged in a task, and you compare it to when, say, you're engaged in a task. and then look at the difference in brain activation and look at the change. And then you can say, oh, it must be that those areas of the brain are involved in doing that task.
Um, I'm going to throw a quote at you. You've probably heard of this quote before. Stephen Hawking said that the brain was essentially a computer and that consciousness was a computer program. Would you agree with this, or would you think it's far too reductive or too simple?
Well, I mean, I would say at some level, the brain is similar to a computer in that it's a sort of computational machine, so to speak. It's just made of organic, biological matter. But if you really bring it down to its basic core, it's a series of ones and zeros. It's like, does the neuron fire? Does it not fire? What is that message is it sending? Right. And essentially it's very similar to how, computers work. Consciousness is I don't know if I would say it's the software. It's consciousness is what the brain does, and not everything the brain does is conscious. So there's a lot of computation, a lot of complex processing that's happening in the brain that's happening outside of awareness that's affecting our behavior, but that's not conscious. So what is the difference between neural processes that are occurring that are meaningful that are not conscious versus those that are conscious? And that's the kind of thing we try to explore. So it's not just, I wouldn't say consciousness is the software, but it's what the brain does. And it's sort of, but it's not everything it does. Some things are conscious, some things aren't.
The neural basis of consciousness, is it still largely a mystery, or have we made much progress in recent years? Because I know for a long time there was no progress at all.
Yeah. Well, again, also in the 1990s, Francis Crick, who was the co-discoverer of DNA with Watson, decided that after his big question was, what is life and the building blocks of life, he figured that out. And then his next big question is like consciousness. What is the neural basis of consciousness? And he, along with a young neuroscientist at the time, Christoph Koch, who's now at the Paul Allen Brain Institute, he was the former president, but they together wrote this paper, I think it was in Nature, that set out to say, look, we can have a scientific discipline that studies the neural basis of consciousness. We can take this legitimately, because until then, consciousness was kind of left to the field of philosophers. It wasn't thought of as a legitimate scientific endeavor to explore the neural basis. But Crick and Koch set out, and because Crick had was such an established scientist, it became legitimate. Okay, you can study the neural basis of consciousness. And they set out this research program. First, they were looking just at vision, at the visual system. So again, it's a young field. It's only been there, for say, 30 years or so. And there has been progress made. There is a big collaborative research project now, adversarial collaboration it's called, where the sort of leaders in the field of the major theories of consciousness, not all of them, there are many theories of consciousness, but sort of the people in the forefront pitted their theories against each other experimentally, and all agreed early on, like, if the data shows X or Y, this would support my theory or the other theory. And we just recently revealed the results of that, of a couple of those studies at NYU at our annual meeting at the Association for the Scientific Study of Consciousness. It was in New York. And the main theories are this integrated information theory of consciousness and the global neuronal workspace theory of consciousness. And the results were not definitive. I mean, there was some, overall, it seemed to lean towards the IIT, the integrated information theory of consciousness. But there's some caveats there, and there was still some support for the global neuronal workspace theory. So we still haven't even landed on a theory of consciousness, but we're learning a lot more about the underlying fundamental principles of like what kinds of neural processes are involved in conscious perception.
But there is an agreed measure of consciousness, the phi. Can you tell us what it does in terms of helping us understand the brain or the mind?
So I wouldn't say it's agreed, but it's within that theory of the integrated information theory of consciousness. So Giulio Tononi, who's a colleague, I was just at a meeting with him 2 weeks ago. He's really the sort of creator of this theory. And then Christoph Koch, who was that original, person along with Crick who kind of laid out the footprints for where this field of the neural basis of consciousness was going. So he supports Giulio Tononi's theory of integrated information theory. Within that theory, it basically, in a very sort of overview kind of way, it says that any system that has a high degree of integrated, differentiated information will have the property of consciousness. And that's just like a sort of like gravity. It's like a property of the universe. The brain happens to be one of these systems. And the measure phi is a mathematical calculation of any system of how sort of integrated this information is. It's a way to measure it. And then that measure would be the amount of consciousness that that system has. So within that theory, that yes, phi, this measure of complexity of information processing equals consciousness, is a measure of consciousness.
And this wouldn't necessarily just apply to human beings. Other organisms within the animal kingdom also would have a degree of consciousness. So the phi would apply to them too.
Yeah, exactly. So one of the interesting, like conclusions of this is that like any system that can have, a certain degree of integrated information. So it's not just humans, it's other animals, but maybe even, plants. And so it's, what they call a panpsychic view. And some people think that's a big flaw of this theory. But theoretically, any system that has some degree of integrated information will have some like degree of consciousness.
I think it's really interesting. There's been a lot of discussion in recent years about trees, for example, and other forms of flora being able to communicate with each other. It'll be interesting to see if there's any research into that later down the line to see if plant life has some degree of consciousness.
And I think plants do communicate in some ways, and there's this whole like root system of like where there's a whole communication between an ecosystem. But whether that has this subjective states of consciousness that we think of when we talk about consciousness, that's to be determined, right? We don't know. Like all I know is that I'm conscious, and that what it feels like for me to like say feel pain or something. I assume that that's what you feel, but it could be very different. And we know from a lot of psychological studies and psychophysiologic studies that, like for example, you might see red slightly different than the way I see red, and we can never really get into somebody else's head. And so that's with humans, you can report whether they're conscious or not. Now, what about animals? How do you measure it in them? How do you report it? And now we get down to plants. It's very difficult to determine, are they having subjective states? Are they having feelings?
If we can move from consciousness for the moment to disorders, can you tell us the difference between neurological disorders and psychiatric disorders, for example?
Well, there's no necessarily hard and fast line between them. So I think, historically, these two fields sort of emerged and were these very like different disciplines, but I think there's a lot of overlap there. And actually for my PhD, I did one of the first studies where I compared neurological brain lesion patients to psychiatric patients on neurocognitive measures. But normally these departments don't even talk to each other, but it's all the brain and it's all interrelated. But in general, when we think of psychiatric illness, we think of it's more of a neurochemical imbalance. And that leads to these mental health issues, to psychological issues from a neurochemical imbalance. But a neurochemical imbalance could be related to neuromorphic differences in terms of receptor sites or number of receptors. It could also be related to the way the brain is wired up. It could be anatomical differences that are related. So like they are neurological in a sense, but historically we would say, yeah, neurochemical differences would be more in the realm of psychiatry, whereas neurology is more of the sort of hardware is, there are deficits and there's a brain lesion or a tumor or, various disorders that have to do with the hardware or the way the brain is wired up. And they're not necessarily psychological in nature. So it could be, for instance, Parkinson's, it's affecting the motoric system, or a neurodegenerative disorder. So some of them do have psychological effects as well, but it's not necessarily having psychological effects with, whereas in psychiatry, it tends to be more about things that have to do with brain dysfunction that result in psychological abnormalities.
Following on from that, then, how crucial is the study of dysfunction and disorders, be they neurological, psychological, or psychiatric, in helping unlock our understanding of the brain?
I think it's critical because when everything is working well in the brain, it's really hard to figure out. Like, for example, your car, when it's running all, everything's fine. You're not really like thinking about like the mechanics of it. But when something goes wrong, and you have to kind of figure out, okay, what is it? The carburetor? Is it this? I don't know. I don't know a lot about cars, but then you can kind of go into the network, into the system, and see how it works and why is this thing going wrong. And that teaches us about how it works when everything's going right. The brain is so complex and it's really hard. When you actually look at the brain, if you see these diagrams of the brain, it's all mapped out. It's like, oh, it's the frontal lobe, the temporal lobe, the occipital lobe, and all these different brain areas. But when you really just look at a brain, the whole cortex looks the same. There's these folds and these sulci and gyri, and but it looks the same. And so to really understand and dissect how it works, it's the best that we've started to do is when things go wrong, you make these correlations like, oh, that. So for example, like a first case was like there was a brain lesion. A guy suddenly he just couldn't talk anymore. And he kept saying 10, 10, 10. This patient, 10, 10, they called him. I think it was the early 1900s, or maybe late 1800s. But they found, oh, he had a lesion in this part of the brain. That's called Broca's area. So when you have a lesion in that part of the brain, we know, okay, that has to do with the production of speech, right? So that's where speech production comes from. Or, then you find someone who's another deficit where they can't understand language. They can speak, they can't understand language. So a doctor named Wernicke discovered that there was a lesion in a different part of the brain. That was Wernicke's area that's involved in speech comprehension. So by having these brain lesion studies, we're able to pull apart like what these different parts of the brain actually do. But we figured out by looking at disorders.
You hosted a Nova series recently on the neuroscience of creativity. What do we know about the neural mechanisms underlying creative thinking and innovation?
Yeah, so I mean, there's this two-part Nova series, and it was really doing an exploration of kind of neuroscience of consciousness in general. And then in the second episode, we focused in on creativity. And well, one thing we know is that these sort of debunked idea that it's kind of left brain, right brain, like, left brain is logical and reason, and the right brain is sort of emotion and creativity. That's not really how it works. While there are some differences between left and the right brain, there is what we call, lateralization effects. Like in general, language tends to be on the left side, but it can be represented on both sides. But we find that there's certain neurocircuits that are involved when a person is being creative. And in particular, parts of the prefrontal cortex that normally like suppress things, like so that our behavior conforms to social norms, or if you have some really odd thought of it, oh no, that's not, that thought is too strange. Let's suppress that, right? But when you're in this creative mode, a part of the prefrontal cortex, the dorsolateral prefrontal cortex, is downregulated and it's decreased in activation. And so that kind of releases the suppression. So it's kind of like, it allows for the novel association between ideas and, kind of like thoughts outside the box. If you were to think like that all the time, it might be maladaptive. It might be someone like with schizophrenia, let's say, right, who's having these strange, odd thoughts. But if you could temporarily sort of open up the box and let the thoughts out and let them, formulate in new, interesting ways, that's where this creativity comes about.
And when somebody is in a state of flow, then is this just an amped up version of this particular phenomenon that you're talking about then?
Yeah. It seems like the flow state. So you don't need to be it doesn't have to be creativity to be in the flow state, but it is one of those things that helps you get into this flow state where you lose your sense of self and time and place. The minute you become too self-aware, you're sort of out of it because you're turning on that dorsolateral prefrontal cortex again. Because that part of the brain also has to do with your sense of self and agency. And so often artists say, like, oh, it feels like it's flowing through me. Like I'm not, I'm just a conduit for this that's coming through, because you don't feel that sense of like I'm the creator in a way. you're in this kind of flow, like you're tapping into something else outside of you. But it doesn't just have to be creativity. It could be, doing a physical activity like rock climbing, or, playing a game of tennis, playing music, but we see that creativity or spontaneous creativity or improvisation is one of those states that help get you into that flow state.
You mentioned it a couple of times there. I was going to ask you about it next as it happens. Sense of self. Do we know
Mhm.
if there's a particular location in the brain that is responsible for giving us that sense of self?
There's not like one area in particular where, it kind of like it feels as if everything is coming together to one place in your brain, and there's this sort of self in there. But it's really a network. It's a brain network that has to do with our sense of self and self-referential information and things like that. But the dorsolateral prefrontal cortex is part of that network that gives you that feeling of self, but it's malleable, and it's our sense of self is based on our past experiences, and it's another kind of cognitive construct that we've created. Like, it's not really real. It's something we create. We have this idea of a self, but we see various disorders where that sense of self can be dissolved. But it seems to be instantiated in a particular neural network in the brain.
And in patients that exhibit disorders where their sense of self has been dissolved, what they're manifesting, is that similar to other patients who will, or other people who will take drugs who then lose their sense of self? Does it represent itself in the same way?
Similar, yeah, it's similar. Or for example, even people who and certain types of meditation can get you to that place where you kind of feel the boundary between self and other dissolves, and you feel connected kind of with everyone and everything. So certainly certain psychedelic drugs can get you there. Psilocybin, which is the ingredient in mushrooms, and you know uh, acid, and then there's more intense things like DMT or ayahuasca, but you lose your sense of self. But you see a similar network that's involved with people who lose their sense of self, whether it's through meditation, flow states, or disorders, like people who have certain disorders like dissociative identity disorder or depersonalization disorder, where they like kind of lose their sense of self, and then it's maladaptive because they can't get it back. They're sort of stuck in that place. Whereas if you're meditating or even take certain drugs, it's temporary, so you can temporarily experience that state, which can be very therapeutic, but then go back to like an adaptive functioning, having a healthy ego and sense of self.
This podcast is called the Happy Habit Podcast because I'm fascinated by the concept of habit formation, acquiring positive, life affirming habits by means of tapping into the brain's neuroplasticity. Now, we all possess this ability to acquire new habits, especially in infancy. But is it true that this neuroplastic capacity never ever leaves us?
Yeah, I mean, the brain is always, it's a dynamic system that's always changing and adapting. That's what it does. We have to be aware of our surroundings and our environments, and change not only what's around us but what we ingest. Our brain adapts. If you start taking a lot of drugs, for example, you're taking a lot of stimulant, your brain's going to downregulate the receptors, and so it's always changing in response to things. And even though yeah, when you're younger, it's sort of more malleable, and it's really receptive to, it's looking to learn and to change and to grow. But up until, the day you die, your brain is always changing and can grow and evolve. It's a little harder. It moves a little slower, the older you get. But so it's less what we call fluid, but it's still malleable. And there's always room for change.
Impulse control is one of your areas of interest. What do the brains of people who aren't good at controlling their impulses look like in comparison with someone who is?
Um, People with impulse control issues tend to have less activation in parts of the prefrontal cortex, like the orbital prefrontal cortex, which kind of suppresses our immediate urges and thinks about the future consequences of our actions. And a lot of the time, we're having these basic basal, like sort of id impulses. I want that pleasurable thing right now, or I want to get away from that unpleasant thing immediately. And then you have then those come from the subcortical parts of the brain, the more evolutionarily older parts of the brain. And then you have the more recently evolved parts of the brain, the prefrontal cortex, which kind of thinks about the future consequences, thinks about, would it be smart to act on this now, or maybe I should withhold responding. And when those systems are in balance, things work properly. But when you have too little activation of the prefrontal cortex, or there's a lesion in the prefrontal cortex, then it's sort of like that brake system is broken, and then the accelerator takes over, and you make these maladaptive decisions, and that's what we see in these impulse control disorders.
And then, as an extension then of that subject, then if we look at people who have addictive personalities or obsessive compulsive disorders, what are we seeing in these people's brains? And also, does the phenomenon of neuroplasticity feature even more so in people with an addictive personality?
So there's some overlap between, so like impulsivity and compulsivity, right? So what we tend to think of as impulsivity is, wanting an immediate reward right now, like not being able to delay gratification, wanting sort of sensation seeking. And whereas compulsivity is more like engaging in a behavior to avoid something negative. But often addiction involves both impulsive and compulsive elements to it, and sometimes it's very hard to differentiate between these two. And so we do see slightly different things in the brain. For example, with somebody who has OCD, obsessive compulsive disorder, it tends to be kind of an overactivation of the prefrontal cortex. They're trying to over control. They're obsessing about something, and so whereas the impulse control disorders tend to be a sort of under controlled. So they're both sort of have a dysfunction of the prefrontal cortex, but in one case it's underactivation, so there's not enough of the brake system, so you're just acting on impulse. And in the other case, it's like overactivation of the prefrontal cortex because of like fear, anxiety. I'm afraid, let's say, for example, of, catching a disease. So in order to control that, and I'm thinking about it all the time, right? Overactive prefrontal cortex, and then ruminating. And then to control it, I'm going to wash my hands, let's say, compulsively over and over again to try to relieve the anxiety. So the compulsion is really something that's done to relieve the anxiety or to appease the obsessions. So it's a slightly different phenomenon, these obsessive compulsive disorders versus the impulsive disorders. But I wouldn't say that they have any more, they're any more sort of neuroplasticity than anyone else's brain per se.
You spoke a couple of minutes ago about psilocybin, and it's now being used to treat depression. But the key is that it has to be taken in conjunction with traditional talk therapy. How does this work, and how is it able to bring about transformation so quickly?
So yeah, we call it, it's psychotherapy, exactly, in conjunction with it's called, psychedelic psychotherapy. And so it's not just about doing the drug in and of itself, it's doing it in conjunction with the therapy that seems to have the biggest effect. And the idea is that, in particular, say with psilocybin, that we're still trying to understand the mechanisms now and why it works, like from this sort of neurophysiologic level. But what we are beginning to think is that it increases neuroplasticity. So it allows the brain to get into a state that it's more open and conducive to change. So when you combine that with the therapy and with the therapeutic suggestions, that patients are more likely to take on those suggestions, and they're going to stick better. The other aspect of it is that some people just have these extraordinary psychological experiences when they're on the psychedelic, and they're transformative, like kind of like when the astronauts have what's called an overview effect, when they see the Earth from afar for the first time, and it changes them forever, their whole perspective. A really great example of this was like William Shatner, the actor who played Captain Kirk on Star Trek, went in the Blue Origin, and went to space for just a few seconds or minutes or whatever it was, but like he came back completely transformed, right? And that's kind of what these drugs do. It's like almost like a shift in consciousness that can help people get unstuck from maybe a really bad pattern of thought that they had been in.
And is it true that the transformation is a sustained one too?
It tends to be. I mean, it's not everyone. And so, I throw in that caveat because I think although I think the psychedelic psychotherapy, it's going to transform psychiatry. And we haven't really had like a big breakthrough drug in, 50 years since, the origin of like SSRIs, but or selective serotonin reuptake inhibitors. So while I think they're super promising and it's going to help a lot of people, it's not, the end all and be all, and they're going to be the cure for everyone that lasts forever. It's just for a lot of people, they take it and they do have these lasting changes. But some people have to sort of have a booster, right? Like they have the changes and then sort of symptoms come back and they need a little bit and they have to do it again. And sometimes it doesn't work at all. So, we have to keep that in mind that it's not going to work for everyone and last forever. But you do tend to see these lasting changes in a lot of people.
Is there any evidence of negative reactions whenever people have taken psilocybin?
There are, and I just was at this meeting with this, it's called the Tiny Blue Dot Foundation that has funded some interesting research in this area, in the area of using of psychedelics and psychedelic psychotherapy. And I was just on this panel about like, what are the potential negative effects of these drugs? Because everyone's talking, so, there's all this hype around it. And yeah, I mean, people can have bad trips, they can have bad experiences, but some, doctors are saying, well, even if you have a bad experience, as long as you're guided and there's somebody there who knows what they're doing that can help you through that you're still going to have the beneficial effects of the drug. But others are saying you might get you might get traumatized by that experience if it's really frightening. And then there was a case of a patient who then started having PTSD from that experience and new anxiety disorders around that. So it's important to keep those things in mind. I think also you have to look at, it wouldn't be a good idea to give these to people who are prodromal or who have the propensity towards schizophrenia, because or has any sort of history of psychosis, that there might be issues there. So there's definitely caveats, and some people can have bad experiences, and we're starting to learn about, we need to figure out exactly who are the best candidates for this kind of treatment and who do we need to exclude, and that's still a work in progress.
Well, staying with novel treatments, especially for depression, a deep brain stimulation, this seems to be very exciting. What does this involve?
So deep brain stimulation involves, these are for treatment resistant depression patients where they've tried the standard treatment and nothing has worked and they're really sort of desperate and at their wits end. And it's a minimally invasive surgery. People get very afraid because of the, horror stories of psychosurgery, at the turn of the century, but or later, but probably the 1950s, yeah, with the lobotomies and things like that. So this is not what we're talking about, but we're talking about implanting these very super thin microelectrodes into these subcortical parts of the brain. For depression in particular, it's in the anterior cingulate, and which we know is like a node in the depression circuit in the brain. It's not like depression's in one part of the brain, but it's a critical node in this circuit, and it stimulates this. And we don't know exactly how or why, if it's like disrupting a faulty network or if it's engaging a network that wasn't engaged before, but it tends to help people with this treatment resistant depression. So, it's connected to a battery pack implanted in your chest wall, kind of the same people who make the pacemakers. And it's just, you can control the stimulation with the normal control. You can turn it up, you can turn it down. There's 4 different contact points. You can play around with which contact points work best along this like electrode. And it's pretty amazing but it only works as long as it's turned on. And what we find is that if you turn it off, even after a few years, or when the battery starts to run out, the symptoms come right back. So it's not really treating it, like curing it. It's just temporarily blunting the effects in a way of the depression. But as soon as it's turned off, right back, the depression tends to come right back.
Fascinating, fascinating. I heard you speak before about the visual system or the visual cortex, and you said at the time that whenever you visualize something in your mind's eye, the same area of the brain is stimulated as if you actually saw that object in real life. Can you tell us how this works?
Yeah, it's dark inside the skull, and the brain doesn't really see anything. It just gets a couple of signals and it makes these interpretations and, formulates a perception. So at some level, whether the information is actually coming in through, say, your eyes, through the retina, and then eventually activating the primary visual cortex of the brain, or whether it's an internally generated idea that then you visualize something that then activates the primary visual cortex of your brain. When you finally formulate an image, say that of a sunset, whether it's internally generated or externally generated, meaning it's out there in the world and it's coming in, the brain, it looks pretty much the same that in the brain, that sort of neural signature of what, say, a sunset looks like. And there's other parts of the brain that determine whether it's coming from being generated internally or externally. But when that is messed up in certain people, let's say in like schizophrenia, they can't tell. So, for example, they'll think something that's internally generated, like hearing voices, they'll think it's externally generated, like, oh, those are coming from outside. There are people talking to me, but really it's your own, it's coming from your own brain, right? But they can't tell the difference. And that I can imagine would be a very frustrating, situation to be in.
You preempted my next question because I was actually going to ask you about voices. We all have an internal monologue or narrator at times, and sometimes it can be quite critical. Where is this voice first of all, and is this voice that everyday people hear, is that voice coming from the same place as the voices that somebody with schizophrenia would have?
Yeah. I mean, that internally generated voice, the voice we have in our head, is pretty much coming from the same place. And it's kind of like auditory cortex. And but we have, with people without schizophrenia, have a sense of like, oh, I know that's coming from my own head. Like I'm generating that voice. And sometimes you can talk back to it and be like, shut up or whatever. But with schizophrenia, it doesn't feel like it's internally generated. It feels like there are people implanting these thoughts, or it's coming from an external world, or someone's trying to talk to them and they're hearing these voices. They don't know where they're coming from. It's really disturbing. But yeah, it would be coming from the same parts of the brain.
If I can briefly move to rumination, is there an evolutionary basis or value to ruminating? Everybody's familiar with lying in bed at night, not being able to sleep because they're fixated on some particular problem or worry. What is the benefit to us as a species to ruminating like this?
I mean, evolutionarily speaking, it makes sense to sort of like that we evolved to be able to like rehearse future threats and like plan for them, right? And so those that could do that would have an advantage, right? If you could think about, okay, so yesterday I saw the tiger behind that bush, so I can imagine it's probably going to come out of that bush today, and then what am I going to do to, prepare for that and whatever. So thinking about potential future threats is adaptive. And there's a whole, field in psychology, of evolutionary psychology, which says that every disorder is basically based on something that had an adaptive function that kind of like went too far or went wrong, or there was like a mismatch in current everyday, world. So, for example, it would make sense if we have a fear of heights, like an innate fear of heights, because those who had a fear of heights wouldn't like fall off the cliff or go off, on the edge of something dangerous. Like they'd get a little nervous and they'd step back, and they're more likely to survive. So that over time, we evolved, more people would have a fear of heights. However, now you're in modern society and you have someone standing on the 50th floor of a building looking out the window, and they're freaking out and they can't, but even though they know logically it's safe, there's still this underlying fear, but it's like mismatched to their new environment, right? And then you get these like quote unquote disorders. But so like rumination is one of those things where it would make sense as an adaptive function to plan ahead and think about potential future threats. But when it goes too far and you can't stop the rumination and it's going, over and over and over again, you can't sleep at night, and then it becomes maladaptive, and then we label it as a disorder.
How much of what we think about, either at the conscious or unconscious level, it comes down to automaticity? I suppose I'm broaching on the subject here about the illusion of free will, but how much of what we think about really is derived as a result of routine pattern thought processes?
Um, a lot. I think a lot of what we do is automatic, and we are running a lot of these unconscious programs most of the time because it's efficient. I mean, if we had to recreate, for each experience and every day, it would be so, you know, inefficient in terms of the energy that we utilize. I mean, our brain uses so much energy and so much of our bodily resources that we need to kind of make shortcuts where we can. And this has, again, an adaptive, it gives us some advantage. It makes sense. However, then you get these things like cognitive biases, which are just shortcuts the brain's trying to use to save energy and time. Um, but most of what's going on is happening on these automatic unconscious programs, and very little of it is it like, oh wait, I'm overriding that, or I have some sort of control. I mean, we do have a level of, maybe not free will, but like a type of self-control that we can utilize. Like we can recognize an urge and then come to a decision to not act on it, and that's a sense of having a bit of self-control. But that's very little of what the brain is doing, and the majority of our behavior is just automatic. Imagine you had to think of every time you got up to walk to go to the bathroom or something, or to walk to the store. It would just be so exhausting. So you just do things, even like taking a shower. You're not thinking about it half the time, or driving. You're totally in another world. Your body's just doing stuff, unless something happens and then it causes your attention to be, like a car cuts you off. But even then, your body's responding before you're even consciously aware of what's happening, right? So a lot of the stuff we do is like autopilot.
One final question, Doctor, before I let you go. What does the future hold for cognitive neuroscience? And do you think AI will play a role?
Yeah, I do. I mean, that's a big question. What does the future hold? I mean, I think ultimately, one of the rate limiting factors is our understanding of just how the brain works, like to be able to intervene and help, treat disorders and things like that, or even prevent them. I think when we get to an understanding of like the genetic basis of our brain development, and if we can even ultimately intervene at the genetic level at some point to, let's say, knock out Alzheimer's in someone who'd eventually, get it, or a psychiatric illness or a neurological, disorder, autism, let's say, for example, or so. I think if we start to understand the genetic basis of how our brain develops, like we can intervene in new and interesting ways. We have the neural implants that I think are going to also be another interesting tool in the field, because not only is it for treatment, but we can do research. We can, those electrodes I talked about not only stimulate these brain areas, but you can record neural activation, and we can learn a lot about the brain, do different experiments. Um, and AI, I think, is interesting because listen, we're already using artificial intelligence. We have been for a very long time, and you know it helps us process data in ways, like I think quantum, computing and things like that are really interesting to help us process large amounts of data to understand this brain, which is this huge information operating system that even with the spy that we spoke about, like we can't even calculate it in like a small like nematode or something, much less in a human, right? So it's because it's so complex. So we're going to need these assistance of tools like AI to help us understand the brain. I mean, the bigger question is like, will these systems be conscious? I don't think so. I'm skeptical about it because I think the software can't be conscious. It's really about the hardware. It's like an actual physical system that creates the information. Like it's like saying, simulating the weather in a computer program and like software, it's not going to actually be wet, right? It's just a simulation. So I don't think like these simulations of like intelligence are going to actually feel something, but maybe if we build a neuromorphic computer that's hooked up the same kind of way the brain is, like maybe that might have something of what it feels like to be something. I think what's really interesting too are these organoids that can grow little like brains in a vat kind of thing, and then they start to develop and form their own connections, and that's really interesting. Maybe they have a little bit of consciousness. We got to think about the ethics of that, So I think there's a lot of exciting things in the field, and people are afraid of technology, but like we adapt the technology and we figure out ways to incorporate it and to use it and to help us understand the world that we're in.
Well, that's the thing. And I've been in many discussions about AI recently, and essentially my conclusion is it's not going away, so we may as well embrace it now.
Yeah, I think people just got upset when it started to be able to like write an essay or something, or like affect the liberal arts students, and then that became more of an issue. But look, I mean, you have to know the field to know For example, I think there should be things in universities where you write a paper, get it to answer a question in the AI system, and then try to find out where it went wrong. What did it not get right? Because if we're going to put all of our trust in these things, like they're not neither are humans, by the way, but we need to be able to discern and to know, like, was this a good answer or not a good answer, and how do we figure that out? So I think there are ways to use these tools and to help us grow and to work around them, because we're going to have to figure out where our place is in the world when these kinds of technologies exist.
Well, exciting times ahead. I love any discussion on the brain, and I've really enjoyed this discussion today. Dr. Heather Berlin, thank you so much for joining me.
Thank you for having me.
Hey there, friends. If you got value from this video, well, you know the deal. Please like, subscribe, share, and I will see you in the next one.